All right. So, I have your quizzes from last time. Anybody have any objection to me just passing them around? Everyone's going to be okay? All right, so. I did post grades this morning. Well, like, I don't know, an hour ago? Okay. Yeah. So let's talk about this problem. I don't know if you remember me trying to make a terrible analogy about this class being kind of like a marathon. Like everyone understands what a marathon is, but it takes, it's different to go run a marathon, right? So this was like, every time I give a quiz, it's kind of like a training day where we go out there and you go and you try and run the marathon. And, some of you are going to make it to the finish line, but not in the time you wanted, and some of you are not going to make it to the finish line. So this problem right here should be able to be done in about 10 minutes, tops. If you realistically have any chance of passing the next test, you've got to be able to do this problem in less than 10 minutes. I mean, that's just the reality of it. That's like me saying, if you're going to finish the marathon in, 5 hours, you've got to finish the first half in 4 hours. You know what I'm saying? Like, I'm telling you, these are like benchmarks you have to reach. So if you're just not there yet, this is just one quiz grade. I'm going to drop at least one. But this will give you an idea of where you are. All right? So if you're not able to do this problem, that just means you need to train harder, which means you need to be doing more problems. You need to be redoing more problems. Yeah. Okay? So what do we do here? And you can't be behind. Of course, if you haven't done this homework yet for this section, then, well, I'm not sure you're cut out for the marathon anyway. You know what I'm saying? You have to train. So, what do I do? I'm trying to give you tough love, okay? I want all of you to do well, but I cannot carry you across the finish line. You have to be wanting to do that yourself. Trig sub, what is the trig sub I'm going to use? X is what? A secant theta. That's right off your formula sheet because we have the formula right here. We have square root of x squared minus a squared. So a for us is what? 2. Right? And now we'll take the derivative. Dx is 2 secant theta tangent theta d theta. And then we also like to figure out what that square root thing is. So the square root of x squared minus 4 is equal to the square root of x, which is this, squared, which is 4 secant squared theta minus 4. Take out a 4, factor that out as a 2, or take that out of the root, and then underneath the root you'll have secant squared theta minus 1, which is a trig identity. That's tan squared theta. So this is 2 square root of tan squared is tan. That good? Now this new integral becomes the square root part, which is 2 tan theta. Excuse me. Over x, which is 2 secant theta, dx, which is just d theta. No. It's 2 secant theta, tangent theta, d theta, right? Your secants cancel, and a set of 2's goes away also. Are you still thinking about that physics test? Okay. You look like you're daydreaming. Okay, so integral, a 2, right? We have a 2 there? Still have a 2? Mm-hmm. So I can pull that 2 out. Integral, I have tan squared theta. And I don't know, is that on your formula sheet, what to do with that or no? Does it turn that into secant squared theta minus 1? It's on the formula sheet? Yeah. It's an identity, yeah. So turn this into secant squared theta minus 1. Now the reason why we would want to do that is what? Why would I want to make tangent squared theta more complicated and make it 2 things? you know the antiderivative of secant squared, and you better know the antiderivative of 1, right? So this is 2 times antiderivative of secant squared is tangent theta. And then the antiderivative of 1 is theta. And then plus c.
Could you have done sine squared theta over cosine squared theta?
Sine squared, you could have, yes. But then what?
Break it up and then 1 cosine squared theta.
I don't know, I'd have to see the work. Could you do what? Skip all that what? And do what? Huh? Did you do something different on yours?
Me too.
Yeah, I'm looking at yours. Look, you could always try and turn this in terms of sine and cosine. You could. I mean, you just, as long as you do everything correctly, yes.
What happens if you took out the 2, or took out the 4 to make it a 2, and then you just square root sine squared minus 1, so it would be sine theta minus 1. And then you distribute the tangent from dx and you cancel out.
I'm not sure what you did. Let me finish this first. Let me, before we
That's what I did.
start talking about all these weird variations. Look, I can usually follow your work and make sense out of what you're doing. And as long as it all makes sense, there are multiple ways to get to the answer. I might look at it and be like, well, that's a little bit more longer road, but you may get to the same thing. So I'll have to look at it. I can't address your issue and you just let me look at your work and grade them. And okay, so now get it back to x, right? So to get it back to x, we use the original substitution, the trig substitution that we made, which was x was 2 secant theta, which means x over 2 is secant theta. Whoa, easy now, easy. And then I draw a triangle, right, based off this. Right triangle, theta. Secant is the reciprocal of cosine. So this should be hypotenuse over adjacent. So hypotenuse, adjacent, and then this side's square root of x squared minus 2 squared, which is 4. Yeah, and this should always appear somewhere on the triangle, right? The thing that we had in the problem, okay. And so now tan theta is this over this, right? And so this is going to be 2 parentheses, tan theta is root x squared minus 4 over 2 minus, now theta, we actually have to come to this and take arc secant on both sides. So the inverse secant of this side, and then when I do inverse secant of secant theta, we just get theta. And so theta is arc secant. William, you see that? You see what you do there? Okay. Anytime you have, your answer has trig stuff with theta, you're going to be going to the triangle. If you just have theta, you're going to have to do some inverse trig function to figure out what it is in terms of x. And then distribute a 2 through. You could distribute the 2 and make that minus 2, and these 2's would go away, and be something like that. There you go. Okay.
So why does the first part of it?
Pardon? You got the first one? Well, I'll be looking for partial credit, but. All right, let's move on. So last class. We started the section on partial fractions. We spent the entire time really just getting prepared for partial fractions, just looking at what we could and could not handle. And now we're going to get into these rational functions. We did the first one last class. So I'm going to start now with the next one, which is b, which is the integral x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. Now, in the problems we did last class, this doesn't look like any of the ones we should know how to do, right? This is not a constant over a linear expression in x. It's not a linear over a quadratic, right? So this doesn't fall into any of those. This is not a trig substitution. This is not a basic substitution. This is not an integration by parts. And it's not a power rule, right? If this weren't here, wouldn't we be happy? Yes, we'd be happy, right? All right, so now partial fractions. Well, we use partial fractions when we see rational functions. This is a rational function, right? And so what we're supposed to do, there was kind of a set of steps. We look at the degree of numerator and denominator separately, right? So what's the degree of the numerator?
2.
The degree of the numerator, I'm going to say degree of n for numerator, is 2. The degree of the denominator is 3. So it says there that if the degree of the numerator is less than the degree of the denominator, that we don't have to do long division. We can just proceed. All right? So we are not doing long division here. We're going to move on. Got it? So what does moving on mean? It means we want to look at this and we want to see first if we can factor anything. So let's see if we can factor any of this. Can we? Let's see, how about the numerator? Does x squared plus x minus 1 factor? If it was plus 1, would it?
Yes.
Yes, it would factor, right? If it was plus 1 at the end, you could do x plus 1 times x plus 1, but it doesn't do that. So how about the bottom? Does it factor? Yes? How? You can pull an x out. That's what factoring is, right? So we can pull an x out. I agree. Can you factor that quadratic any further? Felt good.
Yes.
Yes? How does it factor?
You can do
2x minus 1 plus 2. Do you agree with that or no? No? So what? Negative on the 2? I'm asking you. This is. Does it factor?
Yeah, one of those constants. Take out one of the
Okay, so do you want this one to be a 1?
Yes.
Oh, okay. I thought you said 2x and 2x.
But I think it should be plus 2.
Plus 2 and then.
That's good.
That's good? You sure? 100%? Let's take a vote. Is it good?
Yes.
Everyone's saying yes and no one's. Yes? No? No no's? So it's okay? No no's. Should I check it or no? 2x squared plus 4x minus x minus 2 works. Okay, so it does factor, right? So I'm going to rewrite this denominator like this. So yes, you will need to be able to factor quadratics in order to finish the marathon. Well, hopefully someone's been telling you that since college algebra. You know, you need to be able to factor.
There's a phone app for that, sir.
There is for factoring?
Yeah.
There's a phone app for doing this entire integral.
Yeah. Just use it on the test.
Yeah. Okay, there we go. So that's everything completely factored, right? That's everything completely factored. So what we're supposed to do now is go back to something from pre-cal, which is called partial fraction decomposition. And what we're going to try and do is we're going to try and break this thing up, rewrite the entire integrand as something that'll be easier for us to handle. And so because I'm going to do that, I'm going to completely separate myself from the integral right now and just write down the integrand and do my partial fraction decomposition. So how does partial fraction decomposition work? Partial. Are you answering or question? I'll just call it partial fractions. Okay, that's what I'll call it. What we do when we have an expression that we're going to try partial fraction decomposition on we look at the denominator and we look at each of the factors. X by itself is a linear factor. 2x minus 1 is a linear factor. Understand what I mean by linear, right? X plus 2 is a linear factor. So if all of these are linear factors, what we do is we say that this can somehow be written as this. Okay? That I can somehow take this and split it up into 3 terms. See, these are separated by addition, right? The question for us, and the question back in pre-cal was, is there a way I can figure out what these things on top will be? And I know, because of my experience with partial fractions, that these must be constants. So for each linear factor, I should have a constant over the linear factor, a different constant over the linear factor, a different constant over the linear factor. That's what the first note here says. Cases. Case A, the denominator has n distinct linear factors. How many distinct linear factors do I have here? 3. So for each of the n distinct linear factors, I will put a constant over the linear factor. Now in the notes, I use, instead of a, b, c, I use a sub 1, a sub 2, a sub 3, and then I would go out to a sub n. What's the advantage of using subscripts, a sub 1, a sub 2, a sub 3, over using a, b, c, d? You know, you won't run out of letters, right? So we've discussed something like that before? No, we haven't? Okay. But it makes sense that, you know, if you happen to have this disaster integral that had, you know, 35 distinct linear factors, you couldn't do a over, b over, c over. So you just do a sub 1, a sub 2, and then you would be fine. Pardon that?
36 letters in Russian.
Well, we won't use Russian. Yeah. I wouldn't know what to do. I wouldn't finish that marathon. Okay, so here's where we are, right? All right, so I'm going to stick with A, B, C. I'll use D, E, F whenever we start to get to higher things, because we're never going to go past, you know, like 5 or 6 factors. Okay, break over here this side, we'll never get past. We'll never get anywhere close to like R, all right? So we're good? Okay, so we know that this must be this, and now what do? Anyone? You clear the fractions, and that means you multiply both sides of that equation by the denominator. So you're going to take this and multiply it on this side and on this side. When you multiply this on this side, what happens? Cancels out, and all you're left with is the numerator. And then when you multiply this on this side, it has to multiply, I don't want to write it down, but it has to multiply here, here, and here. So that big old expression is sitting here, here, and here, right? And when it's here, this x will cancel out that x, but the 2x minus 1, the x plus 2 will still be there next to the a. So all I'm going to have is the a, then next to it 2x minus 1, and then x plus 2. And then when I do this one, the 2x minus 1 cancels. I'm left with the b and what other pieces? X and then x plus 2. So x, then x plus 2. And then when I do c, the x plus 2's cancel, so I'm left with c, x, and then 2x minus 1, like that. So that's where we are. We good? Our goal is to figure out what A, B, and C are. Right? That's our goal. Why is it our goal to figure out what A, B was 2x minus? Why is it our goal to figure out what these numbers are? We can integrate. So we can integrate, right? And are we going to have any trouble integrating these? None at all, right? Constant over linear, constant over linear, constant over linear. These are all going to be nice. These are all going to be natural logs, aren't they, when I integrate them? So if we can do the partial fractions on this, we'll be in business. All right, so how do we determine A, B, and C? There's 2 common methods for getting A, B, and C here. There's a shortcut that works most of the time, and there's a longer way that works all of the time. So I think it's worth seeing both. All right, so the first one I'm going to do is the shortcut. All right, so this is the short version of how to do this. The shortcut method is what you try and do is figure out what A is by killing off these two terms. And when I say kill them off, I mean you pick a value of x that will make this vanish and make this vanish, but not make this vanish. So what value of x could I plug in that would kill off this one and this one? X is 0, right? And that won't kill this one off, will it? Right? So I'm going to come in here and I'm going to say right now, let x be 0. All right? Let x be 0. Now rewrite that equation, everything you see, replacing x with 0. What would you get? You include the left side, okay? If x is 0 over here, you get what? Negative 1 is equal to a times 2 times 0 minus 1 is negative 1. And then 0 plus 2 is just 2, right? And then plus, then these are gone, right? 0? 0 plus 0. I don't need those, but just to stress what happened there. And then now this is just an equation, a linear equation in A. Just solve for A. So what is A?
2, or 1/2.
1/2. Negative 1 equals negative 2A. So 1/2 is A. Wow, that was quick, wasn't it? We got A pretty fast there, didn't we? We good? All right, now that we know A, let's go try and get B. So can you preserve B and kill off the A and the C parts? X is what? 1/2. So what you're looking for is what the factor they both have in common, right? This is 2x minus 1, this is 2x minus 1, this one does not have that. So you just need to make 2x minus 1 equal to 0. So if you just do a quick little equation over here, I need to make 2x minus 1 equal 0. So 2x has to be equal to 1, so x has to be 1/2, and then you know what to plug in, right? So I'm going to do that now. Just remember A is 1/2. So now x is going to be 1/2. And, well, this is going to be kind of ugly, isn't it? I have 1/2 squared, 1/4, plus 2 times 1/2 minus 1, right? Equals, yeah, I'll do that after I write everything out. What do we know about this one?
Cancels.
It's going to be 0, right? What do we know about this one?
Cancels.
It's going to be 0. This one, though, I have to figure out. B times 1/2, right? Times 1/2 plus 2. Y'all understand what I'm doing there? Do what? Let's do this side. This together is 1, right? 1. 1 minus 1 is 0. So I still have 1/4 out here. So 1/4 on the left side equals these two together. Please don't tell me 2.5. 5 halves. Okay, thank you. 5 halves. 5 halves times 1/2. 5/4. So this is 5/4 B. And now solve for B. So multiply both sides by 4/5, reciprocal. Both sides, right?
1/5.
Yep. So you get 1/5? Yes?
Yes.
Okay. So 1/5 is B. Okay, we've got 2 of 3, don't we? Now we're going to let x be whatever will kill off these two. So those are the common factors. What makes that 0? X is negative 2. So I let x be negative 2. And then I plug in again. Okay, if x is negative 2, negative 2 squared is 4. Plus 2 times negative 2 minus 1 equals, this one's gone, this one's gone, this one, right, is still here. C times negative 2, 2 times negative 2 minus 1, right? So just be careful there. Make sure you get all the computation taken care of appropriately here. What is this in here? The whole thing right here? Negative 5, and then times negative 2 is positive 10. So the right side's positive 10C, and the left side is negative 1? Yes. Negative 1. So C is negative 1/10. So I have it. I have A was 1/2, B was 1/5, and C is -1/10. Those were both positive? I thought one of those was negative. No? Okay, that's right? Okay. That's it. We've done all the works. It was -1/2? Okay.
The negatives canceled on the
Negatives canceled out.
They did?
Yeah. It was just 1/8.
Okay, so we're good? All right. So that's it. That's what A, B, and C are. So now what I'm going to do is I'm going to go and rewrite the integral. The original integral. That's the integral that we had when it was factored, right? And what I'm saying is that this is the same as integrating three separate things. And those three separate things are a over x. Make sure you go back and look, you know, what was the a on top of when we broke it up? A was on top of the x, right? So I'm going to put 1/2 over x. Just write it like that, even though that looks a little weird. Plus b over, b is what, 1/5? Over what was the factor? 2x minus 1. Plus, and then c was -1/10 over x plus 2. Everyone agree that that's a over x? You know, that's just rewriting? Now, the 1/2, the 1/5, and the -1/10 are just constants, right? I can break this into three integrals now, and those constants can just come out. And that's what I'm going to do. So I'm going to rewrite this as three separate integrals. That 1/2's popping out. 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. Understand what I did? Each one of these is what I said, you know, last class we need to be able to handle. So the antiderivative of 1 over x is natural log of the absolute value of x. So I'm ready to take my antiderivative. So 1/2 natural log absolute value of x. That's the antiderivative of this one. Forget the 1/5 for a second. What is the antiderivative of this? It's natural log of that. Natural log of 2x minus 1. 1/2. Remember, we have to scale out because we have a number in front of x. You see that? We have to scale out that number. So it's the antiderivative of this without the 1/5 is 1/2 natural log of the absolute value of 2x minus 1. But then we had 1/5. So 1/10. 1/10 natural log 2x minus 1. And then here we don't have to scale out by anything, do we? So we just have -1/10 natural log absolute value of x plus 2 plus c. That's it. Just leave it like that. You could combine these together though, all right? Just, you know, FYI, you could, because remember we had properties of logs that if you add two logs together, you can put them together into one log. If you have subtraction between two logs, you can create division. So like you could, if you wanted to, put these two together as a single log with division. You could put that together with that one with multiplication, but it's the same answer, it just looks different, okay? So once we're here, we're happy. Okay? But if you go and you're looking in the back of the book, you're trying to match an answer, and yours doesn't look quite right, just think maybe they did something with properties of logs to get it to look different. What did y'all think?
Not bad.
Not bad? Now, let's look at the longer way, okay? That was the short way. So let's go back to that equation. And I know that you're going to be like, well, I like the short way. And I agree, man. Let's do the short way. Every single time we can do the short way, let's do it. But it does not always work. And so we have to have something to fall back on in the event that the short way fails. So what we had was a, and then it was 2x minus 1 times x plus 2, and then it was plus b, and then it was x. I think this one was x plus 2, right? Was that right?
Yes.
Yes? Okay. So that's it right there. Now, at this point, the long way, what's the difference between the long way and the short way?
Yes.
Well, the long way always works. The short way doesn't always work. All right? And I'll give you an example where the short way doesn't work. Just not yet. We're not there yet. Okay, so the long way, what we have to do is expand this all out. We have to multiply this all together. So I'm going to put first these two together. If I put just those two together, I'll get 2x squared plus, so I'm doing this, right? So 2x squared plus 4x minus x minus 2. And when I put those together, I get 2x squared plus 3x minus 2, right? And there's an a in front of all that. So the a would then get distributed through to that also. So this is going to be 2ax squared plus 3ax minus 2a. Do you all understand where that came from?
Yes.
Yes? Okay, now the left side, I forgot to write the left side down. X squared plus 2x minus 1. Okay, so now I need to do the same thing here. Put these two together, and then I'll pass the b through afterward. So these two together, that's an easier one, right? X squared plus 2x. And then pass the b through that. So you'll have plus bx squared plus 2bx. Notice the way I'm putting these in order. When I multiplied b times 2x, I could have put b times 2 times x. But we like to put, if there's a number, we like to put it in front. Then the b, the x always being the last variable. Notice I did the same thing here. All right, next one. Pass the x through first. That gives me 2x squared minus x. Then pass the c through. So what's my next piece of this going to be? Plus 2cx squared minus cx. All right, now here's why we're doing this. On the left side, we have a second degree polynomial, don't we? We actually know in this second degree polynomial what all the coefficients are. We know the number of x squareds we have is 1, right? The number of x's we have is 2. And the constant by itself is -1. Over on this side, we have, let's see, in our x squareds we have this, this, and this, right? When I put this together with this, I should end up with, if these two things are going to be equal, right, I should end up with 1x squared. So that's what we've got to do. We've got to match the left and right hand sides. But the way I'm going to do it is a little more structured. I'm first going to get all the x squared terms together. I'm just going to write them side by side. 2ax squared plus bx squared plus 2cx squared. So those are all my x squareds, just rearranged. Then I'm going to put all my x terms together. My x terms are these guys. Right? Put those together, so I'll have 3ax plus 2bx minus cx. And then finally, I'm going to put the constants together. Those are the things that don't have x's, right? Which would be this one. Oh, that's it, right? That's the only one that doesn't have an x? Do you agree? -2a. And now here's where I play a little bit of a weird kind of factoring game. I'm going to continue this side down here. I'm going to look at what these have in common. These first three all have x squared, don't they? I'm going to pull an x squared out. Usually we pull the x squared out to the front, don't we? And then write everything else in parentheses. I'm going to actually pull the x squared out to the back. Watch. 2a plus b plus 2c x squared. So this multiplication, remember multiplication is commutative. It doesn't matter what order you do it in, right? So if I put x squared on the back of this and I told you to multiply these, you would pass the x squared through here, here, and here, which is exactly the same as putting the x squared out here and doing it, right? Plus, now on this, what do you think I'm going to pull out of these? X, and I'm going to pull it to the back. 3a plus 2b minus c x. And then finally, I'm going to put the number that's by itself back here, right? That's the only thing left, so minus 2a. Any questions on what I've done? I'm going to write the left side down again. What was the number in front of x squared over here? 1. Okay, so here's what I'm going to do. I know that these things out here, right, if you give me an A, a B, and a C, if you give those to me, this will just be a number, right? It'll be a number in front of x squared. I want that number in front to be what? 1. So I know that this right here has to match up with that 1. Yes? So let me write that down up here. I'm going to write just what we drew there. I'm going to write it down as an equation. I know from that 2a plus b plus 2c, okay, so that's this piece in here, must equal what? 1. Okay. But I also know that 3a plus 2b minus c must match the coefficient of x on that side. So this must be a positive 2. So I'm going to write that down now. Do you see what I'm creating up here? It's a matrix. It's a system of linear equations, right? That's what this is. That must equal 2. And then the last piece of information is that negative 2a, see, it doesn't have any x's, right? So this is just a number. That must match up with whatever the number is over here, negative 1. So negative 2a, and I'm going to write it in order like a's, b's, and c's. Negative 2a must equal negative 1. And this right here is a system of linear equations. And the method to solve this is a method that hopefully you learn in college algebra. But I also see some people breaking out their calculators. I'm okay with you using your calculator to solve a system of equations in this class. I encourage you to learn how to use your calculator to solve a system of linear equations. I'm willing to teach you how to use your calculator to solve a system of linear equations, but you have to come outside of class and I'll sit down with you and I'll show you how to do it on your calculator. All right? Because if you have to do this by hand, it can be done, but it's a little tedious. And look, this is just a smaller part of the bigger problem, right? So we don't want to take 20 minutes on this. Now this one, because this is a pretty simple system of linear equations, I can solve it pretty easily. The reason I wrote that up there is so that you could go back and review. If you need to, go back and look and remember how to do these. There were 2 common methods, but the method that I would look at is called elimination. Substitution is another method, but substitution is really better suited for 2 equations and 2 unknowns. Once you get to 3 or 4 equations, 4 unknowns, and we'll do a problem in here where we're going to have a system that's going to be like 5 equations, 5 unknowns. Substitution doesn't work so great there. When you look at this, though, the system of equations, do you actually know an answer right off the bat just by looking?
Yes.
You know what A is, right? I mean, just look at that last equation. You know right away that A is a half. And that matches up with what we had earlier, right? We got lucky that there weren't any B's and C's in here. If A is 1/2, can't we just rewrite the first 2 now? Okay, so let's just rewrite this system with A being a half. If A is a half, 2 times a half is 1. And so that top equation becomes 1 plus B plus 2C equals 1. And then if A is a half right here, 3 times a half is 3 halves plus 2B minus c must be 2, right? And I don't need to write the third equation because I already used it to solve for a, right? Then I'm going to do a little more work here. I'm going to move this 1 to the other side. Subtract 1 on both sides on this equation. I get b plus 2c is what? 0. And on the last equation here, move the 3 halves to the other side. I get 2b minus c is, what's 2 take away 3 halves? A half. Y'all know what I did, right? Just subtract 3 halves on both sides. Get a common denominator, right? Yes? Okay. Now we're back and we have a system of 2 equations, 2 unknowns, and this is where the elimination comes in, and you can do this pretty quick. The idea behind elimination is to try and get one of these variables to cancel. So I'm going to just go for the b's because they're right here. To make these b's cancel, I'm going to multiply this top equation by negative 2. And when I do that, I have to pass the negative 2 through the whole thing. So I'm going to pass negative 2 through the top, get negative 2b minus 4c equals negative 2 times 0 is still 0. And then the bottom equation, nothing changed. Does this look familiar? You remember doing this at some point in your life? Okay. Now that I've done that, what do? Add these 2 straight down. So if I add those 2 straight down, what equation is left? So gone. Negative 5c is equal to 1/2. And to get c by itself, divide by negative 5. And if I divide by negative 5, it's the same as multiplying by the reciprocal. I'll get negative 1/10. Wasn't that what c is? Yes. Once I know what c is, I can go back and get b. And I can do it by plugging in c here or here, anywhere I want. Any equation I could plug it back into. So I'm just going to grab this one right here. I'm going to plug c as negative 1/10 right there. So 2b minus negative 1/10 has to be equal to 1/2. So 2b plus 1/10 equals 1/2. 2b equals, okay, take 1/10, subtract it on both sides. What's 1/2 minus 1/10? Oh, the wheels are about to come off. 4. 1/2, take away 1/10. Common denominator? You could get a common denominator of 10, so multiply top and bottom here by 5. You get 5/10 minus 1/10. 4/10, yes, but 4/10 is 2/5. All right, and then divide by 2 on both sides or multiply by 1/2. You get b is what? 1/5. Is that what we had? Yes. We have a, b, and c. We go back and we do the integral now. Okay, that's definitely the long way. We want to avoid that at all costs, but we will have to use it. I mean, we will be willing to use it when we need to. All right? Questions?
Is there a way to identify when you'll need to use the longer way?
Yeah, you'll see what's going to happen is, you know how we were in the short way, we were trying to be clever the way we picked x, and we tried to pick an x that would kill off everything but what we were looking at, like what we wanted to find. You won't be able to do that. When you try and kill something off, it winds up killing everything off. And then you can never isolate one of them. And in that case, that's when you have to go the long way. You'll see it. I'll give you an example. Let's go to the next problem, C. Next problem, x to the 4th minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1. X cubed minus x squared minus x plus 1 dx. So you look at the degree of the top, you look at the degree of the bottom, right? The degree of the top is bigger than the bottom. So I have to start with long division. Okay, that's what we have to start with. So let's go ahead and do that. X to the fourth plus 0x cubed minus 2x squared plus 4x plus 1. So because the numerator was missing an x cubed term, I made sure that I put some space in my long division for that x cubed. And then I'm going to come out here and put this denominator. And then you're asking yourself, what do I multiply x cubed by to turn it into x to the fourth? X. And you could put the x down here, like above the x's if you want. It doesn't matter. The answer is up here. So x. And then that x gets passed through to each of these, right? X, 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 all the way through. So x times x cubed is x to the fourth. X times negative x squared is negative x cubed. See, that's why it's important to have that space for the x cubes. X times negative x squared, and then x times 1, which is just x. You come through here and you subtract this, which means you change all the signs. So this becomes a minus, this becomes a plus, this becomes a plus, and this one becomes a minus, right? And then you add everything down. And what are you left with if you add down? So nothing. X cubed minus x squared, because you have negative 2x squared plus 1x squared. 4x, take away x is 3x. And then finally, 1, take away nothing is 1. Am I done? Yeah. No, I have to keep going, right? You're going to go and keep doing long division until the power here is bigger than the power here. Right now, it's not bigger. It's the same. So what do I multiply x cubed by to get x cubed? 1. So I put plus 1 here. And then I pass it through again, right? Pass 1 times this, 1 times that, 1 times that. So what do we have here? X cubed. Sorry, I can't really. Change the signs. Right, change the signs, add down. So what do I have? 4x. That's it, just 4x? Okay. 4x. So you come up here and you put R 4x, right? No. What do you do?
4x over what
You add the remainder over the divisor, right? Okay, that's it. That's the long division step. That step's done. So this original integral really turns into the integral of this, which is x plus 1 plus 4x over x cubed minus x squared minus x plus 1 dx. Now, have things gotten any better for us? Yeah. A little bit, right? We actually have 2 pieces of this that we can integrate right now, couldn't we? We could integrate that. Let's go ahead and do that. Can I erase this? You want to keep this up here? What's up? It's gone? Okay. All right, so this becomes 1/2 x squared plus x plus that integral, right? Changing colors here because I want everyone to realize that this is now our problem, all right? This is what we have to work on. This is the piece that's going to require the partial fractions, right? Everything else we've already got an antiderivative for the first two pieces. Now we're focused on this. And so we're going to try and do partial fractions on that. So I want to start by seeing if I can factor the denominator. Does this factor? Let's talk about that over here. Does x cubed minus x squared minus x plus 1 factor? How many terms do you see? 4?
Minus 1 squared and x plus 1.
So how are you doing that? What is that technique that we call factor? It's a factoring technique. It's factoring by grouping. If you have 4 terms, you can try it this way. You split it right down the middle, right? And you try and factor a GCF out of the first 2. So what factors out of these?
X squared.
X squared. So I have x squared, and then what's left there? X minus 1? Yeah? And then what you have to have over here is you have to be able to factor something out here of these two so that what's left in parentheses matches that exactly. Can you do it? Negative 1? And so x minus 1 here? Do you agree?
Right.
Once you have this, once these match, then what? This is just x what? X minus 1 times x squared minus 1. Where did the x squared minus 1 come from? These two pieces, right? So factoring by grouping. Does that factor any further? That's a difference of squares, isn't it? That's x plus 1 times x minus 1. And x minus 1 times x minus 1 is x minus 1 quantity squared. So this is really x plus 1 times x minus 1 squared. That's what the denominator is. Yeah, so let's see how this is going to work. This is going to be a slightly different case, all right? We good? The bottom factored. So I'm going to now be working on this integral. Remembering, I'm going to come back to this. I'm not going to drag this along with me the whole way, all right? This is really 4x over x plus 1 times x minus 1 squared dx. Now what we did in the previous problem is we had worked on it and we had broken it down to 3 distinct linear factors, right? 3 different things. You remember what they were? It was x on the bottom. We had x, 2x minus 1, and x plus 2. Remember that's what we had on the bottom of the last one? And so we did a over x, b over 2x minus 1, c over x plus 2, right? That's because we had 3 distinct, meaning different, linear factors. Here, I have 2 linear factors, right? These are distinct. They're different. X plus 1 is different than x minus 1. This is a linear factor. This is what we call a repeated linear factor because it's squared. That means a repeated. And the way that you do a repeated linear factor with partial fractions is a little different than the way you do just a linear factor by itself. So here's how it works. You go like this. Let me just start. I need more room. We're at the partial fractions step. Okay, so for partial fractions, I'm just working on the expression. I'm not going to be working with an integral right now. I write down the partial fraction I'm going to be working with. Now, for that first x plus 1, since it's just a linear factor, it's not repeated, I can do a over x plus 1. That's still what you would think. This next one, though, you would think would be this, right? b over x minus 1. bx, you think you want to square that, right? Well, this is the proper way to do it is to put b over x minus 1, then another one, c over x minus 1 squared. Okay? So what if this had been the third power? I would do b over x minus 1, c over x minus 1 squared, plus d over x minus 1 cubed. As many as you need. So if this were to the fifth power, it would be b over x minus 1, c over x minus 1 squared, d over x minus 1 cubed, e over x minus 1 to the fourth, f over x, right? As many as you need. And if this would have been squared also, then you would have done a over x plus 1, b over x plus 1 squared, then c over x minus 1, d over x minus 1 squared. So that's how we handle it. And that's what the note says, but it's hard to read that note and understand that that's what's happening. Yes?
What if the 4x was squared?
We don't even care. We don't care about this at all. The only thing that that's going to help us with is when remember when I did the long way and we were trying to match the left and right hand side coefficients? That's all this is going to contribute to it. All right? Okay, so that's our breakdown. And now we try and find a, b, and c. So last time we multiplied both sides by the denominator. So I'm going to multiply this side of the equation by this, which means all that's going to be left over here is 4x. Equals, now when I multiply this times all of this, I don't want to write it in here, but I guess I'll do it just for this one. X plus 1, x minus 1 squared. What cancels out? X plus 1, so all I'm left with is the a, and then x minus 1 squared. Agreed? When I do the x plus 1 times x minus 1 squared, only one of the x minus 1 factors cancels. So I'm still stuck with the b. The x plus 1 is still there, right? And one of those factors is still there. And then on this one, x plus 1, x minus 1 squared. The x minus 1 squareds do cancel, and all you're left with is c and then x plus 1. Understand? Questions?
Do you know why they do that?
Why what?
The x minus 1, then the x minus 1 squared, when you only...
Why we do that? Because it'll work. Yeah, I know that's not the answer you want, but I mean, when you're coming up with the method for partial fractions, right? When that method was being created, I'm sure that it was attempted to try and just do like this one, b over x minus 1 squared. And you just couldn't get to the numbers that way. So just kind of a trial and error thing. I'll look into that a little more. I don't think that there was like a formal process. I think it was more of like trial and error. I'll look into that. That's an interesting question. Because, well, as we move on, we'll see like the factors down here dictate what we put over there. It's a linear factor, a over it, right? If it's repeated linear, we do like b over it and then just keep on bringing the powers up. But if this turns out to be a quadratic factor that doesn't factor, it's like an irreducible quadratic, then we do something different. So, all right. What are we going to try and do? Short way? You want to try and do the short way? Is it going to work? Why isn't it going to work?
Two of the terms will cancel.
2 will cancel. Let's just go after a first. Let's just see what happens if we get a, if we try for a. If we try for a, we need to kill off these two. Can you kill off these two? What can you? No?
Because B has one from each.
No, I'm saying if I'm trying to get a, can I kill this and this at the same time without killing that? X is -1?
Oh, yeah.
If x is -1, will it kill this one off?
Yes.
It will kill this one off?
Yes.
But it will not kill this one off, right? -1 minus 1 is -2. So it looks like we can get a, can't we? So let's let x be, what did you say, -1? Okay, so